we're going to look at Chapter 10, Folds and Folding. The first thing is to cover some basic vocabulary so you can understand what I'm talking about when I talk about a fold, or if you read about a fold in your textbook or a journal article or anywhere. Table 10.1 in your textbook, page 241, has a full list of terms. I'm going to go over the terms that I feel are the most important key terms, things you might see on homework or a test or something like that. The hinge area. This is the region of greatest curvature that separates the two limbs. We'll tell what limbs are in just a moment. But you can see here the hinge area is right along the top of this fold. It's the most bent, most curved part of the whole fold. The hinge line is a line right along that point of greatest curvature. In this case, it's a straight line. Sometimes a fold will have curves and bends in it horizontally as well, and so the hinge line will be a bent or curved line. A limb is the portion of the fold that's less curved. So it's less curved than the hinge, but usually still has some curvature. Portions of it might be straight. An inflection point, just like in math classes, an inflection point is where the direction of curvature changes. So above this inflection point, we have a concave downward, or basically, it curves up and over the top. At the inflection point, it's changing to a concave upward, where if this continued, we would have a bowl shape where it's curving upward with a hinge down. So the inflection point is right where it changes from concave up to concave down. Or if the hinge is oriented differently, it wouldn't be an up and down, it might be a left and right. A fold axis is a line along the fold that tells a general direction of it. Generally drawn along a limb. It could be along a hinge, so it could match up with a hinge line. But this fold axis is one long line along the limb, anywhere along the limb, that goes along, and you can tell if the fold is cylindrical, which we'll talk about in a moment. It'll be a straight line. If it's curved, then you have other things. But then the limb is basically made up of a whole bunch of these fold axes all along it that make up the whole thing. An axial surface connects all of the axes right through the hinges. So if we have a hinge line of this layer, and a hinge line of the layer an inch below it, and a hinge line of the layer an inch below that, and an inch below that, all of these lines will make up a general surface. And it's an imaginary surface because there's nothing physically going through it like that, like we have drawn here, but that surface that you can draw, three-dimensionally, or with computer software draw it three-dimensionally, connecting all of the hinge lines is called the axial surface. Sometimes they are actually straight lines, and then you get an axial plane. If they're not quite straight, which is more common in the real world, then we just keep it an axial surface instead of an axial plane. A profile plane, on the other hand, can always exist. You don't have to worry about anything in the real world being straight, because what it is it's your cross section where you chopped across the fold, pretend or for real. Maybe there was a road cut, maybe you're just imagining to do your drawing, but it has to be perpendicular to the fold at that point. So if your fold is curving, that profile plane is still perpendicular right where it's drawn. And it gives you the cross-sectional shape of your fold. So we have a profile plane drawn right there. However, right at this edge where you see all these lines and labels and so forth, basically there was another profile plane, and we just removed what was in front of it so that you could see this. Now you can see the shape of the fold. That's what the profile plane is for. Now, within the bends of the fold, we can use the same terminology that we use for waves. Waveforms in physics, waveforms in mathematics, the same terminology. So here we use the symbol rho, looks kind of like a lowercase p, and this is the interlimb angle. So it's the angle between the two limbs. So in this case it looks to be approximately 120 degrees. The capital L with a subscript lowercase a is arc length, so for length of arc. And basically you go trough to trough, or you could go peak to peak. But it's the length across it. So if this were exposed as a hill and you were going to walk it, how far would you walk going all the way up and all the way down? Which is different than the wavelength, which is equivalent to map distance. So like if you were looking at a map and threw a ruler on there and said, oh, this is 2 inches, and on the scale that means it's 1 mile. Well, okay, that's the map length, equivalent to the wavelength. Again, trough to trough, peak to peak. But the wavelength is always shorter than the arc length, because for the arc length you have to actually go up the hill and down the hill. Now, amplitude, this is a lowercase a amplitude. It is half of the height. It's basically from baseline, like a 0 level, to a peak, which is also the same as that baseline to the trough. So this is a lowercase a amplitude, and sometimes you might be more familiar with an uppercase A amplitude that goes all the way from peak to trough. So this is half of that. It's a lowercase a amplitude. And it's important to note that the line from, like if this is 0 elevation, say this is 10, and that makes the trough -10, the width of the fold right there is 1/2 of the wavelength. So L sub W divided by 2. And that height there to the peak gives you lowercase a amplitude. On the other hand, if we go all the way down to the trough from the peak or the crest, both peak and crest are appropriate. So from the crest all the way to the trough, 2 amplitudes, 2 lowercase a, then the width of the fold is the wavelength. So you can see here wavelength, and then arc length. You can see the trough, the crest or peak, and then 2 amplitude and 1 amplitude.